Before we continue with the lesson, I suggest you to practice worksheets 2A to 2C that apply the equation for the general design allowable level it always greater than or equal to actual level, or actual level less than or equal to allowable level. So with that confidence, let's move on to the new topic, which is load deformation. Want to find out the relationship between the load and the deformation, and how that diagram that represent that relationship look like. So before we get into the diagram, I want you to look on the video of that demonstration with the rubber band, the blue and the yellow, before we continue. You see, to demonstrate the load and deformation diagram, the relationship between the load and deformation, and we have two rubber band, the yellow one and the blue rubber band. And as you can see, for the yellow band and the blue rubber band, both have the same thickness, but the width of the blue band is basically twice at the yellow band. So from that, if we cut that cross section for yellow and the blue, then the cross sectional areas of the blue band is at twice as much at the yellow band. So with that, let me apply the load to get the deformation. The first one for the smaller areas, cross-sectional area, which is the yellow rubber band. So if I want to get the deformation from here to throughout of the screen of the camera, you see my bow end here, and it look very easy. So the load in there, it will be P. Then if I apply the same load P for this rubber band, and as you can see, I just go that much. If I want to get the deformation throughout the width of the camera, what I do, I have to take more load. It basically, it's 2P in here to get the load and get the deformation that I wanted, which is through the width of the camera. So as you can see, that the relationship between the deformation and the load, it depends also on with the same material properties, which is in this case the rubber, but the cross-sectional areas also detect that relationship, and that you will see the diagram that I'm going to draw in the lecture. So as you see the demonstration for the load and deformation relationship with the two yellow and blue rubber bands. Now if I can draw the diagram to show that relationship, here is if we have the diagram for relationship, the vertical, it will be the load P. So basically the load, so the one that I apply in my hand, and then the deformation of the rubber band. So that deformation, we call that a delta, and that called delta, and it was assembled in inch or in centimeter, millimeter, etc. Depends on the unit system we have. So the areas for the blue band, so let's call that area is EA. So we can, if we cross section of that areas of the blue band, we can have something like that. Let's put in 3D. So we can have that here. Rubber band. You see that? So same thickness, and that it will be, we call it that 2A, or let's call it A areas of the cross section of the blue rubber band. And the relationship that we apply here is the more we increase the load with my hand, then we increase the deformation. So that's nothing new, and that's the first scenario for the blue rubber band, that we can call that here C1 relationship, the curve number one. And the yellow rubber band, the smaller width, so the one, let's put yellow, a little bit smaller there. The thickness still the same, so you have that. So the areas of that one now is 0.58. 0.58. Look like a firework in when I draw the yellow in here. So with that, as you can see, I apply smaller load. The deformation will even as much at the blue rubber band. So the curve number 2, which is for that yellow rubber band, it's go down somewhere here, and that I call C2. So as you can see, because that apply smaller load, the deformation will increase even more. So that's why the C2 is lower than C1. So if we have, assume I don't have it, another yellow band, not yellow, but let's call that is, with the color I have, let's call it black rubber band, and the area increasing double at A, so it will be like that. If I cut that rubber band and that area is here, is 2A, then of course you will make it harder on your hand so that you can extend that rubber band. So that curve relationship for that can be go in that location, and C3 is in there. So as you can see, we apply more load, but the deformation it will be less. So as you can see, at any given load, let me demonstrate here. At any given load, for example, there you can see the deformation are not the same. For the yellow, it tends to deform more than the blue, a little bit less, and then the black with have the highest cross-sectional areas, it even deform less. So as you can see, different delta in there. So as you can see, even the same material, the deformation are not the same, the geometry are not the same. So from that, as you can see, that disadvantage of this is, I can write down here, disadvantage of this load deformation diagram is the disadvantage is that every geometry has a different curve, right? So you see geometry with different cross-sectional area, 0.5A for yellow, A for blue, and 2A for black rubber band. So is that every geometry has a different curve. Even the same material in this case is different curve. Same material, rubber in here, but as you can see, it's a different curve in there. So that's not a good thing. So because of that reason, we introduce a concept called normal strain in this class. So let really the concept we are talking about when we see the relationship between the load and deformation is not good when they have different curves even with the same material. So normal strain, and for normal strains, it called that is epsilon, and read down, spell out at epsilon. So from this one, let me make a case in here. So if we have a cantilever with the fixed support at one end, so the original length we call it L naught, and then if we apply a load P, to the right, then of course it will deform. It will extend, elongate the length of that cantilever. So it become a position. Let me see it in here. Can show that it will deform just like a rubber band that I show you. Yeah, I just exaggerate that, but that it will deform. And if we apply the load P, that make this body in tension, load P. And the final length after the load applied that we call it is the LF, final length. And the difference between the final length and the L0, the original length, that we call it a delta deformation, something that we draw in there, in the load curve up there. So delta. So that's the deformation delta. So from that, if we call it epsilon, in this case, is the epsilon is the normal strain. Normal strain. And what is that about? It equal to the deformation over the unit length, of the body, unit length. So what does that mean? In equation, we get the normal strain, epsilon, it equal to the deformation, delta, in that case, as you can see, and it equal to LF, the final length after deform, and then minus L0, the original length, over the original length of the bodies. The difference between LF and L0 is delta, which is the deformation, and that is delta over L0. What is the unit here? As you can see, LF minus L0 or delta is inch, millimeter, etc. L0 inch, millimeter, feet, etc. So from that we can have the unit. You see that is no units, but for this one we call that a inch over inch. So it's basically 1, right? But that we should specify that at the unit of the normal strain instead of put no unit. Or in the matrix system, we can call that a millimeter over millimeter. And why we use small unit for the distance? Because as you can see, normally the deformation is not that big. If it's big, already the body, the structure is in failure already. So let's go to some important concept of the of strains before we continue. So let the importance of strains. Of strain. So first, serve at the design performance criteria. So serve as a design performance criterion. So this strain is too big, you can visually see the structure in deflection or elongation. That's not good. Then you need to limit that deformation, and in this case realize at a strain. So that one of criteria for the design. And even we already study the stress, but for strain it's easy to measure, and you will see that in lab number 3 we basically measure the strain and then transfer to the stress. So let's talk about this one. It'll be more easily to measure. We can apply the strain gauge into the body structure to measure the strain. So easily measure than stress. And then the next important point, it adds in the analysis of the statistical indeterminate structure. What is that about? We will talk in next week. So it will be added in the future lecture, add in the analysis of statistically indeterminate structure. Just give you a very quick what is the statistical indeterminate structure here, but we will talk about that in the future lesson. So if you can be able to use the engineering mechanics that you learn to solve the external reaction. With that, we call it determinate structure. So it had when you draw free body diagram completely correctly, then you have enough equation to solve for the external reaction. For indeterminate structure, you have to use the deformation deflection equation to solve. If you only use the equilibrium equation in engineering mechanics, you cannot be able to solve the indeterminate structure. And that's why we need to study mechanics of material. So that difference between determinate and indeterminate structure. And then the last important point that we want to emphasize, which is the stress and strain curve, the relationship with the, for example, normal stress, normal strain curve, is independent of geometry, independent of geometry. And that's a good thing compared to the load and deformation. As you can see, it depends on the geometry. Even the same material, C1, C2, C3 different if the geometry, in this case cross-sectional area, are not the same. So but for if we introduce the strain, then the curve, the stress and strain curve, is independent of the geometry. So that will be a unique for certain material. For example, if we talk about the rubber, that curve, stress strain curve, is unique for that material. So with that, what it look like? Let me continue with that important concept. So that is the normal stress, normal strain curve. Normal stress relationship, normal strain curve. So what is the normal stress? So the stress created by the normal force perpendicular to cross-sectional area. Normal strain, so for example, the cowl member, centric axial loaded members, the normal strain is the basically the strain along the longitudinal axis of that cowl member. So same at the same direction of the normal stress, if you want to say that. So here for the curve, so let's draw for a generic any material. They have a unique normal stress and normal strain. And for normal stress, we will put it in the vertical. Normally, for example, KSI or Pascal, etc. And then the horizontal, it will be epsilon. And epsilon, as you can see, if it in customary units, that inch over inch. So what is the typical behavior for one material? So let me draw it general like this. So at the beginning, the relationship is straight, so it's linear relationship, and then it go up top, and then it a little bit fall down, and if you could continue to apply the load at some point, it will be fail. Basically the material broke, and that point we no longer, after that, no longer load stress can apply to have elongation because the material already broken. So with that, you can see there is two zones of behavior that we are talking here. The portion, initial portion, basically that is a linear, portion, and that we call it elastic region, and in that elastic region, if we release the stress, the strain and also release go back to original length. And now after that continue, we can call that a plastic, or we can say inelastic. So for any behavior after elastic region, so at elastic region, as you can see, the curve is linear with the epsilon and sigma. If after that, it will be plastic. So if it pass the elastic zone, the material it cannot get back to the original length or original geometry after you release the stress. So from that, you can have the blue line in there. So basically that we call it normal stress and normal strain curve, sigma and epsilon curve. And for that curve, it will be independent of geometry. So it does not depend on what is the cross-sectional areas as we do in the load and deformation diagram up there. So it will be say independent of geometry. Of geometry. And it's unique for each material. It's unique for each type of material. So for example, rubber, steel, aluminum, etc. So it's material. It's unique. So unique, if I compare, for example, each of us have a fingerprint, and the fingerprint of you and I are not the same. It's unique. My fingerprint are unique. Your fingerprint are unique. That's same for the sigma and epsilon curve. It's unique for a material. So from that, we can consider just like a fingerprint, right, of the material. So basically, if we see the curve, sigma and epsilon curve, we can be able to interpret what that material is, fingerprint. So with that, we stop this video, and for the next video, we'll introduce the other concept, and from continue with the sigma and epsilon curve, and then we talk about Poisson ratio later.